Okay, so our last speaker for this session will be Monika Trymoska. She's presenting their work, Shifting Our Knowledge of MQ Sign Security, co-authored with Lars Rahn.
Yes, thank you. And thank you for staying for this last session and see what we have prepared. So yes, I'm going to first tell you what MQ Sign is, and actually it is very convenient that I had Sophia talk before because it is a UOV-based scheme. So yeah, I was counting on the fact that she would cover some of the basic construction, and then I'm presenting an attack on this one. So yes, MQ Sign is a round 2 candidate in the Korean post-quantum cryptography competition, so KPQC. This is a competition, so not a standardization process, of course, but the main goal was to have many new original research in post-quantum coming from South Korea. And one of those new research, also focused on chems and signatures, same as, in the NIST competition. One of those new research outputs was this MQ Sign digital signature scheme that is based on UOV, but has a more structured central map. And so, the goal there was to have a smaller secret key. And in this work, I'm going to present a universal forgery attack on the variant that passed to the second round. And it is going to be an algebraic cryptanalysis attack. So that's why I'm going to give you like a small introduction of what is algebraic cryptanalysis, right? So this is a cryptanalysis technique where you take your description of the scheme, you take your public key, the message, anything that you can, your input data. And then you model the problem of the attack. You model it as the problem of solving a multivariate system of equations. Okay, we will see some examples of modeling today, specifically modeling MQ Sign. And then once you have the system of equations, you give it to an MQ solver. And this can be either a Grosvenor basis solver, or for smaller fields, you have exhaustive searches or satisfiability solvers and so on. And then you get this solver will give you a solution to the system, which will correspond to the problem that you were looking for. So either the secret key sometimes, or maybe your goal was to forge a message. Okay, and in this case today, here you can replace the scheme with MQ Sign. So we're going to attack MQ Sign, and what we're going to see is a forgery. Okay, so a bit more about MQ Sign. Well, first I need to tell you that, I'm going to use the matrix representation of quadratic maps everywhere, right? So this is how you switch from, if you're used to looking at equations like this, then the representation of this equation in quadratic maps form, in matrix form, would be, you put all of the coefficients, let's say this gamma I j, you put the half of that coefficient in the ijth entry in the matrix. And so if you do this, actually, you see that if you multiply a vector here with this matrix in the middle that represents your quadratic map, and you multiply it with the vector also on the other side, you get exactly this polynomial. So that is why this symmetric matrix represents exactly your quadratic map. Okay. And so, for instance, this is what a UOV central map looks like, right? You remember in UOV, you had the split of the set of variables in vinegar variables and oil variables. Here I put the vinegar variables first. Some people prefer the other way around. But if you put the vinegar variables first, then it means here, everything is covered except for this oil part here, which is always 0, right? Because you have in UOV that oil doesn't mix with oil. So you don't have monomials containing 2 oil variables. And so in MQ Sign, it's going to be very similar. So you have this, but you also have some additional structure in the gray parts that I have here. So in UOV, everything would be random, right? And MQ Sign also has a completely random version of it, which corresponds to UOV. But here I will use this drawing to kind of tell you what the different parts are. So I'm going to call this the vinegar part, right? The part where the monomials containing 2 vinegar variables stand. And then I'm going to call this the vinegar oil part. So oil and vinegar variables. Okay, so now about a little bit more about MQ Sign, because maybe it is, I don't know if you've seen this scheme before. So it started, the submission of MQSign started with the start of the KPQC competition. I don't have an exact date there, but it was November 2022. And then, yes, MQSign was one of the submissions here. And then the first attack on MQSign, so this one was round one submission, a little bit different. So it was, the specific structure that it has was sparseness. So the central map was very sparse, and so it means that there were a lot of coefficients that we knew. And then we had an attack on this one in 2023, March. And so we attacked two of the variants, specifically those variants that had sparseness in the vinegar oil part. And this is with other co-authors, so Thomas Olbach and Simona Samardziska. And then quickly after that, so we also used some other property of MQSign, that mainly that it uses this equivalence key optimization that I will talk a bit about later. But yeah, we were relying on that, and then very quickly after the attack, there was another attack that also kind of managed to remove this requirement that MQSign is using the equivalent keys optimization. And then after this attack, so yeah, the MQSign team announced that they will remove these faulty variants that have sparseness in the vinegar oil part, and only two variants remain. So one that is has a structure in the vinegar part, and one that is completely random, which is UOV. Okay, and then we also managed to attack the other structured variant, so the one that has sparseness in the vinegar part. And eventually, yeah, MQSign went to the second round of the competition, and they had a new design, they had a new proposal. So they had this other submission, and again, the second author changed there, so now it's Shim and Kwon. And I'm going to talk about this variant today and how, yeah, what we did to attack it. Okay, so these are the two MQSign variants that remained, that were proposed in the second round. So you have the MQSign LR, that is the structured variant, and here, as I said, the vinegar oil part is completely random, right? That they saw, we saw previously that having a structure in the vinegar oil part is really not a good idea. And you will see why in one of the next slides. And then the vinegar part is defined exactly like this. So you have this circulant matrix, here x1 to xv. And this is without coefficients in front, right? This is only the variables. And then here you have a shift to the right. You have the last coordinate, xv, and then it continues x1, x2, and then the next row is another shift, and so on. And here on the other side, you multiply with this matrix whose entries are linear combinations of your variables. And this is how you get the equations in your central map, okay? So that is the structured variant, right? The one that is takes less space, but it is more risky in terms of security. And then they also have the more conservative variant, which is, yeah, where both the vinegar and the vinegar oil parts are random. This is equivalent to the classic, you know, the mathematical description of UOV. It differs from the UOV NIST submission in the up to implementation choices and so on. So in this work, we will attack this variant. So another thing that I need to tell you about MQSign is, yes, this equivalent keys optimization that I've been talking about. Actually, it is very well known for UOV that you can, yeah, if you have, let's say, starting from one central map, the way that it is constructed, you have the central map that is very structured, it is easy to invert, right? And then you have an isomorphism to another map that is supposed to be random looking, right? And the isomorphism is via this invertible matrix, right? It is a linear transformation on the input variables. And so, given yes, from a central map, you apply S on both sides, right? If you are looking at the matrix representation, you need to multiply with this S on both sides, and then you get a public map P, right? But from this public map P, there are many, many possibilities for the combination of S and F, which are your central map and the isomorphism, okay? So mainly, the people have found in the literature that this is always an equivalent key that exists, right? So when you're, from an attacker's point of view, you can always just attack this key, right? So then people also started implementing UOV using this as an optimization, meaning our transformation on the input is going to be this matrix, and this is stored in fewer bits. Okay, and there are some side channel analysis attacks on this. So yeah, this is, with implementation, you need to be careful about using this. Okay. So specifically what this means for key generation, okay, so now you see also an example of how key generation works. If we apply the key generation using this specific form, we obtain exactly this as a public map, okay? And specifically here you see that, yeah, you don't need to look at the other entries, right? I divided it block by block. Specifically, you see that the upper left corner of the public map corresponds exactly to the upper left corner of the secret map, okay? So it means that this is completely public information, this part of the secret key, right? And that is why I've been telling you having a lot of structure in this other part is not a good idea because that is a crucial part. This one, it shouldn't matter too much. At least knowing what the coefficients are shouldn't matter too much, okay? That's why it was harder to attack at first. And then this is also something that we are going to use. So we are assuming that we know exactly that the upper left corner of the public map corresponds exactly to the upper left corner of the secret map. Okay. So how do we forge a signature? First, let me remind you. So what would forging a signature mean here? What is the goal? So the goal is to find this vector, and I divided it here in block matrix form in vinegar variables and oil variables. So you need to find the vector that satisfies this equation, right? I wrote it here in matrix form. Meaning this is a pre-image of your public map P, okay? And for a given target vector, so you want to sign, let's say, this target vector. Okay, so if I rewrite this nicely in one equation, you see that this is what I obtain. And specifically, I notice here that I have only vinegar variables here, right? Here I have vinegar times oil. Here I have, and the P will be a constant, right? The P is the input. And here I have only oil variables. Okay, so next thing that I can do, this is a system of equations with V plus M variables, right? And you have only M equations. So you can easily assign V variables randomly and expect to have a solution. This is how it works in UOV signing as well, like Sophia told you. And so here we choose, because we see that this part here has only the structured part. So we choose to assign everything that is in XM to 0. And we get exactly this equation, right? And here, the P1 has this specific structure, so that is what we're going to use. So we need to find a solution for this very structured system here. Okay, so with the toy example, let's start getting used to knowing how these maps look like. So this is how let's say this is a small example, a toy example with M equations and 8 variables. By the way, these are not good UOV parameters, right? This is just the balanced UOV, but here for a toy example, it's better to look at it this way. And I'm going to focus on this target, let's say the 0 vector. So if I multiply this, I get, this is what I get for the first equation, right? And behind this else, it's a linear combination of the variables, if you recall. So that's how I get the first equation. To get the second equation, I multiply the second row with this vector, so I get the second equation. Then this is how I get the third one. This is how I get the fourth one. So this is the system that we are dealing with. This is the system that we need to solve now. And I will focus on this target before showing you a generalization in the following. Okay, so let's see what this looks like in matrix form, right? Because this will, this is the first thing that we did. Looking at it from matrix perspective, and you will see immediately how, it gives a better insight on the structure of the system. So if I write this equation in matrix form, remember this was, I denoted here the rows corresponding to, the different variables and also the columns. So this here is the coefficient of x1 squared. This is x2 times x1 over 2, and here you have the symmetric one, and so on. Here I'm not going to do a canonical representation. You will see why. So for instance, if I want to store this, I want to store the first equation in this matrix, right? So I have x1 times L1, which is, recall this, x1 times this linear combination here. So here it is very easy to fill in the first row, right? This is everything that x1 multiplies with, right? So this will be, the first one will come here, the second one with x2 will come here, the next one here, and so all of the others here. So specifically notice that here I just filled in the first row with the linear combination L1, right? I can just replace it like this. It's a bit of an abuse of notation. L1 was the linear combination, right? Imagine you're mapping to the coefficient vector. And then if I look at the second monomial here, x2 times L2, Well, that one, actually, I can just plug in L2 in the second row, and then again, same for the X3, and same for all of the rest. So this is the matrix corresponding to the first equation. Okay, I'll put it aside, and then let's do the second one. Right, so here I have X1 times L2. So that means I put L2 in the first row here, then I have X2 times L3, and so on and so on. So yeah, this is what the second equation looks like. And you notice already, yeah, that there is some structure appearing. So mainly I have almost the same thing here, but L1 jumped down all the way down here, and everything else went up. Okay, and this trend continues if you look at the other equations. So to form now the third equation, we just need to copy the second one and then do a permutation like this, while putting the first row at the end. And then same thing for the fourth equation, you just copy the third equation and then you permute the first row. I mean, you permute all of the rows, it's a cyclic shift. Okay, so that is the structure that we're dealing with. Specifically for our forgery, what does this look like now? So here this is the equations that you have usually for forging a signature in UOV, right? But here I can just replace it with everywhere. Instead of having a different equation here, P to the 1 to the 2 to the M, I can always keep the first equation, P to the 1, and then just add a permutation on the left, right? Because this is what we have. Okay, here T, yeah, it's the permutation matrix that corresponds to a cyclic upward row shift. And actually, yeah, in our example, if you want to know what this permutation matrix looks like, it's exactly if you take the identity, you permute the first row. So this is the matrix that we are multiplying with. Okay, so let's do that now. This is the first view, right? The first view of the problem is that T permutes the rows of the quadratic map. And so, yeah, this is multiplied by the identity, the first equation, then you do the permutation, so this is T times P1, and then you do this again for the third equation, so you get T squared times P1, and then you do it again for the third equation, so you get T to the third times P1. Okay, so that is one way to look at your equation. So this is, yeah, you have the 4 equations that you need to satisfy with this vector here. But an alternative view would be to kind of, yeah, this is associative, right? So I can just imagine also that T, instead of multiplying the P matrix, it is multiplying the X vector that is on the left, right? So in that case, and here it multiplies on the right, so it's going to be a permutation on the columns. And this is exactly the permutation that it corresponds to. I checked this for you. And so, yeah, so that is X times T. And then you permute again, so you get X times T2. T squared, sorry, and here you see that this equation remains the same one. If you do this again, you get exactly, yeah, the fourth equation. So what we notice here, this is the key point, right, is that, yeah, I can either try to find a vector that satisfies all 4 equations, or I can try to find a vector that actually satisfies only one equation, but also, yeah, also the permuted versions of it on the one side. So it's not exactly the permuted vector. Okay, but one thing that we notice is that if we have a vector that is invariant under permutation, so for instance, all of the coefficients are the same, right? You have 1, 1, 1, 1, 1, or 2, 2, 2, 2, 2. Then that vector, if it is a solution to the first equation, it will be a solution to all of the equations, right? So those kind of vectors that have a period in them, that have a subsequence, a repeating subsequence, they have a better chance to satisfy all of your equations, or at least they need to satisfy fewer constraints. So this is what we're going to, yeah, this is going to be the main idea of the attack, right? And yeah, I only mentioned the repeating 1 period vector, but now, yeah, it is the same thing if you have like a repeating 2 vector. Here I switch the color so that you don't have to keep track of the coefficients. So again here, yeah, this is the second equation that needs to be satisfied, right? But then if I do this one more time, then you see I'm in the configuration where this vector is the same as this one, so it is the same as the one in the first equation. So basically we're done, right? If you manage to find a vector that has this period and satisfies the first 2 equations, then you satisfy all of them. And it generalizes to a 4 periodic target as well, right? So you do the permutation here. And then I will add another equation here, actually. So this 5th equation doesn't exist, but imagine if you had a 5th equation in our example, which you cannot see here, then you you are back into your first configuration, and this is like a 4 periodic vector. Okay, so we're going to look for solutions that look like this. And notice here that we obtained these repeating equations. I mean, we were able to reason like this because we were solving for the target omega equals the 0 vector, so we always needed the equation to evaluate to the same value, right? This is not true if your target vector is completely random, of course, then you don't have the same equations even if you have a repeating solution, right? But it does generalize to, other periodic targets. For us, the 0, 0, 0 was a 1 periodic target, right? But it can also be a 2 periodic and so on and so on. So this is the generalization. If you have a d prime periodic target, where d prime also has to be a divisor of v, v is the length of your vector, so the number of Wiener variables, remember? We can look for a d periodic solution for any d that is a multiple of this d prime, right? The period of your target. But as long as that d is also a divisor of this v, which is the number of variables, okay? That is what you need. And here I'm saying, it's again an abuse of language here, that I'm saying it is a d prime periodic target. Actually, it doesn't have to be completely periodic. You can have fewer equations than, and then it doesn't matter, you can fill them in. So for example, I'm giving you here an example with MQ sign security parameters for level 1. So this is what we had, right? Having a 1 periodic target, like the 0 vector, we can look for a 1 periodic, 2 periodic, 3 periodic solution, and actually we were very lucky with MQ sign parameters because this 72 has a lot of divisors, so we could try a lot of things. But yeah, if you have a 2 periodic target, then you can only do vectors that are multiples of 2. If you have a 12 periodic target, you can only do 12, 24, 36, and so on. And for these remaining ones, you only have one possibility. Let's see. Okay, so we will call such d prime periodic targets weak targets, and I'm going to talk about how many we can solve. Okay, so a basic outline of this algebraic attack is that we build the system, and this is the system that we need to solve, right? And notice here that I'm going from t to the 0 to t to the d minus 1. So I have d equations in d variables that I need to solve. And I'm not going to go into more details about the resolution, but yeah, we are using a hybrid approach, so some enumeration, and then finding a Grosvenor basis, so FXL. And we have an improved guessing strategy because of the structure that these systems have. That is not what I chose to talk about. So now, how do we turn this into a universal forgery attack, right? Because this was only for some weak targets. Well, if you recall, this is like the trapdoor construction of how UOV, or trapdoor-based signatures are created. So basically, when you are signing, you need to sign for the hash of the message concatenated with some salt, right? So this is going to be your target, and on the signer side, you can do this easily. On the verification side, you need to compute whether this is the case. So if you're an attacker, you need to find a pre-image of this omega, of this W, actually, here. So it means that we can result, actually. Yeah, this is the idea for the overall attack. So for a chosen D, right, you choose D as far as you can go in terms of computational complexity. And then for that chosen D, you need to choose randomly the salt until you find a D periodic target, or a smaller one, right? That would be even better. Once you find such a weak target, then you can solve the system of equations. If the system has no solution, then actually this is the bad news. You have to resolve again and do this whole thing again until you find another weak target, because this one didn't have a solution. But if you find a solution, then you're done. And you've managed to forge a signature. Okay, so I'm going to shorten a bit the complexity explanation because I have like a minute left, or 2 minutes. So this is the overall complexity of the attack, where you can see here, this is the complexity for solving the system of equations, and this is the complexity for computing one hash, and they sum up, right? Because you need to do first the hashing, and then finding the weak target, and then solving the system. And then this is the probability of the resulting system having a solution, and this unfortunately is a multiplication in the complexity, because you will have to resolve if you don't manage to find the solution. And here are the complexity estimates for the 3 levels of security of MQ sign. So you see that it doesn't quite reach the level of security that we want, but it is still an exponential attack, right? If because we are counting also this is for the universal forgery attack, right? For forging a weak target, there are some weak targets that you can do in less than this. And be careful with these complexity estimates that we have, because we compute this complexity of solving the system under assumptions for semi-regular systems, right? The system is very structured. We needed to look more closely if we wanted to do serious business, like choosing parameters. But yeah, this is very tough work, and it was actually, the systems are solved a lot faster in practice than this, but yeah. So careful with this, yeah, complexity analysis is not good enough for parameters choosing. Okay. So in terms of countermeasures, yeah, I don't have very good news here. So mostly, yeah, we're proposing to choose V prime, right? Then you have very few, yes. If you choose V prime, then the only weak targets are the one-periodic targets, right? But you still have to deal somehow with this in the protocol. And yeah, I don't know if there are any provable security people here that you can tell me whether this is, good to reject these weak targets signatures or not. Yeah, I don't know if this is manageable. So now that I told you everything, I can just complete the timeline here. So yeah, this the attack comes here in the timeline, November 2024. Yeah, the 20th of November 2024, and then after that, so the competition was closed closely after. So MQSign didn't win the competition, but it was still one of the best contenders. So actually, if I may comment a little bit on the structure, it was a very well thought of structure in terms of avoiding all of the generic attacks. These are very ad hoc attacks that we had on the very specific structure that is really unexplored before. So that was everything. Thank you very much for your attention, and I will take your questions now.
Okay, are there any questions? Please.
Hi, Monica. Thanks for the presentation. It's really great. This is quite intense. I really appreciate the timeline. In your paper, I mean, you detailed weak targets and a successful forgery attack. I'm curious, did the MQSign team give you any feedback, or will they, change the parameter choices? Or I know they've ended, but did you hear from them?
Yes, so usually, for the previous attacks, we did have a lot of communication, and they were responsive, and they really did listen to our, the cryptanalysis advice on that, and they removed the targets. Here, it was very close to the competition, so I don't think that they wanted to maybe give something very concrete, right, close to the end. So I don't know what is the idea now, and that was actually, yeah, one of my closing points was to invite you all to kind of look at the structure. Is very interesting. So I don't know if, yeah, just having these countermeasures would work, but yeah, I would definitely like to see this further. So, and I don't have news from the team what they are officially planning.
Okay, any other questions? So your attack relied on this cyclic shift they had for defining part of the interesting part of the matrix form. I'm assuming this would generalize to having other structures in there similar, like if it was like a block cyclic shift. It seems like a similar process would work, but then maybe you would need to have your period be a divisor of both, so maybe that might be something else that forces you into this one periodic regime, if that makes sense. I'm also curious, is there any other place you can push this? Any other types of structures that you think you might be able to have similar techniques for addressing?
Yes, yeah, I see what you mean. So the structure part is really the public part. So technically, it should be known. There's no reason to not have another structure. Yes, I haven't thought about what it would be like if you have just block shifts. Yeah, I don't have a visual exactly if this would work at the moment. You can definitely break the periodicity only by, like you said, having. It doesn't need to be even like a prime number of variables. If you have something that, for instance, for us, we managed to do the attacks always with V over 2. That one is a very good balance for both the hashing and the solving. If, for instance, V is odd, then you need to do V over 3, and then your hashing has no chance to hit a weak target. But still, yeah, I'm not sure whether these are good directions to go into in putting the structure, because there are still the weak targets, even if it's not a universal forgery attack. There are still weak targets that you know in the protocol that you must not accept. So then how do we handle this in the protocol? I don't know yet. Yeah. But about the block question, I haven't thought about it. That's interesting.
Thank you. Thank you. Okay. If there are no other questions, let's thank the speaker again and all the speakers of the session.